Have you ever walked past a dull, cracked rock, white, dirty, lifeless, and thought, there's nothing special here? What if I told you that rock could be hiding pure gold, invisible to the naked eye, locked deep within veins of quartz or woven between layers of ancient schist? Rocks so common that prospectors once stepped right over them? Today we'll uncover why ignoring these rocks might mean walking away from a fortune. Nature doesn't label her treasures. Gold doesn't always gleam in sunlight, waiting to be noticed. Sometimes it hides, trapped inside milky quartz or buried within dark, banded schist. These aren't just ordinary rocks. They are geological vaults, silent witnesses of Earth's most violent transformations. Pressure, heat, time, that forged gold itself. In this cinematic journey, we'll explore the secrets of quartz veins and schist rocks, how they form, why they matter, what clues to look for, and how generations of miners have missed or mastered the art of recognizing them. So, before you ever toss aside another boring rock, let's learn what nature might be hiding inside it. Quartz. It's the second most abundant mineral on Earth. Transparent, milky, sometimes smoky. Yet beneath its modest appearance lies the most reliable clue to natural gold. When hydrothermal fluids rich in silica and metallic ions travel through cracks in the Earth's crust, they cool, crystallize, and leave behind veins of quartz. As those fluids slow and solidify, heavier elements like gold are trapped inside, sometimes in microscopic flecks, sometimes in dazzling veins pure enough to see without magnification. Imagine magma pushing upward from the mantle, forcing fractures through ancient bedrock. Superheated water, saturated with minerals, rushes through these cracks at immense pressure. As the fluid cools, silica begins to crystallize into quartz, sealing the fractures like nature's own cement. But here's the secret. Gold doesn't dissolve easily. It travels with sulfur, chlorine, or tellurium in chemical compounds until sudden temperature or pressure drops force it to separate. That's the moment, the golden trap, when flakes, wires, and nuggets become embedded within the quartz matrix. So what you see as a simple white vein cutting through a mountain might actually be a frozen record of this elemental drama. Every sparkle, every fracture could hold micro deposits of native gold. Now, not all quartz is gold-bearing, and this is where the trained eye matters. Look first at color and texture. Milky quartz with rusty iron stains or dark mineral inclusions often points to mineralized fluids. Hematite, pyrite, and chalcopyrite are faithful companions of gold. A quartz vein showing iron oxidation, the rusty reds and browns you see on old rock faces, tells you that sulfur and iron once flowed here, and that's a strong indicator that gold could have tagged along. Second, structure. Gold doesn't appear randomly. It aligns with geological fractures, shear zones, fault lines, or folds in the surrounding rock. Follow those lines. If you find a quartz vein cutting across schist or granite, especially one with visible iron staining, you're standing on potential gold ground. Third, sound and density. A prospector's hammer can tell more than you think. Gold-bearing quartz feels unusually heavy because of the metallic inclusions. When struck, it sometimes gives a dull, loaded sound compared to the sharp ring of pure silica quartz. Experienced prospectors recognize it instantly. Throughout history, quartz has been the stage for some of humanity's greatest gold discoveries. The legendary Mother Lode of California, almost entirely quartz-hosted gold. The Witwatersrand Basin of South Africa, the richest goldfield ever found, began as quartz pebble conglomerates. And in the Australian outback, massive quartz reefs still yield specimens where pure gold veins snake through white stone like threads of sunlight. What's remarkable is how ordinary these rocks look from the outside. Rough, grayish, sometimes dirty with clay. But break one open, and it might glimmer with flecks worth thousands. Now let's move deeper, literally, into Earth's metamorphic heart, schist. Unlike quartz veins that form from hydrothermal fluids, schist tells a story of transformation. Rock reborn under heat and pressure so intense that its minerals align like pages in a book. Within those layers, gold often migrates and concentrates. When the original rocks, sedimentary or igneous, undergo metamorphism, their minerals recrystallize. If those parent rocks contained even small traces of gold, schist can act as a sponge, trapping and remobilizing it into concentrated zones. Picture ancient ocean sediments rich in iron, silica, and trace metals, buried for millions of years beneath mountains. As tectonic plates collide, heat builds, and the rock transforms into schist, flaky, glittery, with visible micas and biotite layers. During this process, fluids move through the rock, dissolving and redepositing minerals. If those fluids carried gold, they leave microscopic films or visible streaks along the foliation planes, thin golden lines that sparkle when sunlight hits at just the right angle. Unlike quartz, schist doesn't show its gold openly. It hides it, sometimes chemically bound, sometimes mechanically trapped. But experienced geologists know that when you find schist adjacent to quartz veins, the combination is explosive. The quartz vein feeds the schist, both literally and economically. So how do you know if the schist in front of you could hide gold? Start with color and luster. Schist that shimmers with silver, bronze, or golden flakes is rich in mica or pyrite, both positive signs. Touch it. If it breaks into flat plates and reveals tiny metallic glints under sunlight, you might be holding part of a metamorphic gold system. Look for quartz stringers, thin white veins running through the darker layers. Gold often travels along these microscopic fractures, especially near contact zones between schist and intrusive rocks like granite. When explorers search for gold in schist terrain, they rely on a combination of geological mapping and intuition built on observation. For example, the Yukon Territory in Canada are classic schist gold environments. Prospectors often follow what they call feather lines, the intersection between quartz veins and schist foliation. These are nature's fault-controlled conduits where gold-rich fluids once flowed. If you're panning near such areas and see fine golden dust or black sands rich in magnetite, trace them uphill. They likely originate from weathered schist or broken quartz nearby. Behind every visible nugget is a chemical story. Gold doesn't form randomly. It needs heat, pressure, and time, and quartz and schist provide all three. In quartz, gold crystallizes from hydrothermal fluids. In schist, it migrates and concentrates during metamorphism. Over millions of years, erosion exposes these once-buried systems to the surface, scattering flakes into rivers and soils. The very placer deposits people pan today. So the next time you see a milky vein crossing dark bedrock or a flaky schist glinting under your boots, pause. What looks like a lifeless rock might actually be a fragment of Earth's hidden treasury, a geological diary of fire and pressure written in quartz and schist, sealed with gold. Most people overlook these rocks. They see white quartz and think ordinary. They see schist and think ugly. But in geology, appearances deceive. These rocks are not just stone. They're the storytellers of Earth's gold-making process. And those who learn to read them, who understand their signs, hold a key that prospectors and miners have chased for centuries. Because in nature, gold doesn't shout. It whispers through the cracks, it hides in plain sight, and only those who look closely will ever hear it. This is EGS, where nature reveals her richest secrets, one rock at a time.